Let's talk a little bit more about chemical bonds. First, let's review what happens when an atom gains or loses electrons. When an atom gains or loses electrons, it becomes an ion. An ion is an atom that has unequal number of electrons and protons. If we look at sodium, its electron configuration is 1s2, 2s2, 2p6, 3s1. That's 11 protons and 11 electrons, so 11 positives and 11 negatives. But when sodium loses an electron, it loses its 3s1, you now have 11 protons because the number of protons in the nucleus doesn't change, and you only have 10 electrons. So it's plus 11 charges and minus 10 charges. So you have a plus 1 charge left. This means that all ions will either have a positive or negative charge. Look at the electron structure of the sodium ion. What neutral element has this electronic structure? The 1s2, 2s2, 2p6. A neutral atom with 10 electrons also has 10 protons. So the element number 10 is neon, which is a noble gas. Which noble gas is each of these ions? So take a look at lithium. When lithium loses its 2s1 electron and becomes a plus 1 ion, it has the electron configuration of 1s2. This is the same electron configuration as helium. Nitrogen will gain 3 electrons. When it gains 3 electrons, it becomes a negative 3 ion. Therefore, it has a 2s2, 2p6 outer energy level, which is the same as neon. Oxygen has a negative 2 when it becomes an ion, and that electron configuration is the same as neon. So ions begin to look like noble gases when they become positive or negative, lose or gain electrons. The rule here is that ions begin to look like a noble gas. Noble gases have a filled outer energy level. They look like this. This is why noble gases will not react, because they're very stable with their outer energy levels having 8 electrons in them. Here on this picture, we've taken the periodic table and we've wrapped it around. So we've taken the left side and wrapped it around to meet up with the noble gases. Lithium over here, when it loses an electron, its electron configuration moves towards heliums. In the third period, magnesium and sodium will lose electrons to become the neon electron configuration. But in the second period, oxygen and fluorine will gain electrons to have an electron configuration like neon. And this continues all the way down the periodic table. So as each of these become either positive or negative ions, their electron configurations will be that of the noble gases. And that's because the noble gas configurations are stable. Let's see what this looks like in a little bit of practice problems. Here we have sodium. It loses 1 electron. It's 3s1 right here. Loses that. So it has a plus 1 charge. Magnesium, to become a stable noble gas, sorry about the writing there, it will lose this 3s2 and become a plus 2 charge. Fluorine, on the other hand, it's easier to gain 1 electron than to lose 7. So it gains an electron here, giving this outer energy level, and it'll have a negative 1 charge. All of these ion configurations here are noble gas configurations. And that's the whole point of bonding, to become stable. We talked about electronegativity in the student presentations. Electronegativity will be really important for us when predicting what type of bond will be present between 2 elements in a compound. Let's discuss polar covalent bonding. So what does it mean that one end of a molecule has a higher electronegativity? What we're looking at here are bonds between non-metal elements. So that means the electrons are shared between the two. So it's important for you to keep that in mind. We're not transferring electrons, we're sharing. So here, between carbon and oxygen, here carbon's electronegativity is 2.5, oxygen is 3.5. What this means is that oxygen is electron greedy. It will keep the electrons towards its side of the molecule more often. So the electrons are drawn this way, and if the electrons stay over here more often, this side will become partially negative, and the carbon loses, so it will be partially positive. Over here with nitrogen and hydrogen, you see the difference. Nitrogen is greater, so this is our greedy side. The electrons will stay over here more of the time, so they'll be pulled towards the nitrogen, leaving hydrogen partial positive. Between carbon and magnesium, this here is a bond between metal and nonmetal. Between carbon and magnesium, carbon is able to actually pull the electron from magnesium. So magnesium will be positive and carbon negative in terms of their charges. The electrons here will be distributed unevenly. So one side will keep the electron more of the time. So what does it mean that a molecule is polar? One end of the molecule has a higher electronegativity than the other end. So here, for example, with hydrogen and chlorine, which is hydrochloric acid, you're going to notice that hydrogen has a 2.1 electronegativity and chlorine has a 3.0. So chlorine will pull the electrons to its side more. So over here it's a very high electron dense side, and this side will be positive because the electron will not be over at that side of the molecule as often. You're going to have bonds between two elements that can be polar. You can have whole molecules that are polar. As a result, the electrons will be pulled unevenly. So the electrons will be over here again more often than the hydrogen side. So how do we predict the bond type? How do we know what type of bond will form? Typically, we will look at whether it's a metal and a nonmetal or a nonmetal bonding. Metal, nonmetal, we can pretty much be sure that it's going to be ionic. Now, in some cases, depending on what type of nonmetal, there may not be an ionic bond that's formed between the metal and nonmetal. But those are exceptions. For the most part, in our use, we're going to believe that a metal and a nonmetal will always be ionic. Polar covalent occurs between two nonmetals, and it will have a difference of 1.69 and 0.3. A covalent, just a standard covalent bond, is a difference between 0.0 and 0.3. So let's take a look at a few examples. Let's start with a diatomic. We'll look at fluorine, F2. Fluorine is two fluorine bonded together, so they're both nonmetals. Each fluorine has an electronegativity of 4, so it's going to be 4.0 minus 4.0. So this will equal 0. So diatomics are just plain covalent bonds. There's no polarity to them. They are sharing. So in other words, they share the electrons evenly between the two elements. If we look at hydrobromic acid, we're going to have hydrogen with bromine. Both are nonmetals. And here we're going to have 2.1 minus 2.8. And you want to take the absolute values. We don't care about negative signs. So this will be 0.7, which according to our chart is a polar covalent. This will be an uneven sharing of electrons. Bromine will be a little greedy and the electrons will stay to this side. So bromine will be partially negative and hydrogen will be partially positive. If we take a look at NaF, sodium fluoride, we have Na, which has a 0.9. Well, let's draw our molecule first, or a compound. So this is a metal, nonmetal. This will be a 0.9 minus a 4. So we get 3.1. Again, absolute values. We don't care about the negative sign. This would be an ionic compound or an ionic bond. So in this case, the electrons are transferred between the two. Knowing the scale can help you in situations where, mostly with nonmetals, where you don't know for sure if it's polar, covalent, or covalent. And you'll have plenty of time to practice these with some WebAssign questions. Now that is the end of our Chapter 8 Video 1 lectures. There were 2 parts, Part 1 and this was Part 2. Everything that you need to answer questions on the first WebAssign should be in these first 2 videos.